The doctor Neil Pederson, he comes from Harvard Forest, from Harvard University, from United States. About his biography, the Dr. Neil is a forest ecologist at the Harvard Forest, studying the dynamics of all-growth forests from individual trees to regional and subcontinental scale. The Dr. Neil earned an associate degree at SUNY Morrisville, a bachelor at SUNY FF, a master's degree at Auburn University, and a PhD at Columbia University. Before the Harvard Forest, the Dr. Neil was an assistant professor in biology at Eastern Kentucky University and a research professor at Lamont Doherty Air Observatory. The Dr. Neil has studied climate change and disturbances ecology in Mongolia, Bhutan, China, Spain, Turkey, the Republic of Georgia, and over much of the eastern US. Currently, the Dr. Neil is studying the impacts of extreme climate on the life of street in the northeastern U.S. forest and all growth forests in the U.S. The topic that he will speak in this conference is related about the following. Influencing ecological theory via cross-dating. Ecological cross-dating is hard. So you are welcome, dear professor, for this conference. I will permit that you can share your PPT. Okay,
Okay.
you can start, please.
Yes.
You're welcome.
Okay. How's that? Okay. Good morning, good afternoon, good evening to everyone, wherever you may be, this wonderful first Ecuadendro conference. Congratulations to Kelly and all the other organizers to putting together a fun and unique opportunity to talk about tree rings with people from all over the world. My talk is on cross dating, which is a very basic thing, but I'm going to try to convince you it's extremely important even for understanding the ecology of our forests. And towards the end, it might even get a little philosophical, but I want you to know that this is all based on a lot of data and study and research. So to that end, I need to acknowledge the thousands of trees that I've been fortunate to study from and to learn from about their lives and the lives of a forest. To the many, many people who have helped me in the field, in the lab, mentors, colleagues, students, anyone that I've learned from and assisted with my research. I'm really grateful for their time and effort and thoughts. And to the organizations that have allowed me to pursue some of my questions and research and interests. I'm very grateful to all for these opportunities. A big question to me is what is the ecology of the 21st century forest going to be like? We know climate change is changing rapidly. It'll continue to change over the 21st century. How will our forest respond? And I think that's a really open question with a lot of uncertainty um, that dendrochronology has already contributed to, not the uncertainty, the knowledge, but I think we can actually do more. And so before we get into cross-setting, I want to talk about how we can contribute to studying the ecology of forests. And so this is a scene from a couple autumns ago in the southwestern Adirondacks in New York State. This is an old growth forest, mixed species. Maybe there's 7 or 8 species in this forest. And in the upper left corner, you could see the large eastern white pine, Pinus strobus. Pinus strobus. Laura Smith, my former research assistant in the blue tank top, is standing in front of it. In days past, when I was younger, when I was doing different things, that might be the only tree I core in this stand. It's big, it kind of looks old maybe, but to study the ecology of forests, I can't emphasize enough that we need to study all the trees or as many as possible. We can't study all the trees in this forest, but it's really important to understand the medium size eastern hemlock, the black cherries, the yellow birch, and those that are in the understory or the mid-story or in the top of the canopy. We need to study all of them to understand what the 21st century ecology in these forests might be like. And there's a wonderful paper, almost 14 years ago, essentially mathematically 14 years ago, I don't know what time of year it came out, by Marco Carrar, where he gives us a model and kind of implores us to start studying individual trees instead of chronologies. So again, when I was younger, I did what a lot of people do, and I would take a mean chronology for a particular species. I'd understand the climate response, and I'd start talking about the ecology. And what Marco shows here in this figure is that's not the full reality of what's happening in the forest. So he has the standardized correlation of individual trees in the small black circles of a population in two different seasons, and then larch or larix in June and July on the far right. And you'll see that the mean chronology, especially of the pines, is doing what we think we do when we make chronologies, what we know we do when we make chronologies. We distill the individual variation of trees into a mean chronology. And in the case of pine, for dendroclimatology, this is great. We make a stronger correlation versus climate versus the population. In larch, it's not as extreme, but it's still much stronger than most of the trees in that population. And what I want to argue here, what I want you to think about is we need to understand the full range of the climate response in the populations that we study to better understand the 21st century ecology. And I am going to belabor this point. I want to walk us through some hypothetical outcomes of doing this kind of research. So this comes from a paper that a bunch of us published back in 2020 to get some insight into internal population dynamics of Atlantic white cedar in terms of growth particularly, but I think we could apply this to several ecological processes related to trees. And what you have here is in orange, we have population A, and in blue, we have population B. And what you have under these curves is the range of population, hypothetical population that you can't see, with their correlations distributed along the x-axis. And so what you see is population B, most of the trees are skewed to the right to a correlation between, 1.5 to 2.5. Population A, the orange population, is more evenly distributed across this spectrum. There are trees that respond strongly negatively to any particular climate variable, whether that's temperature, VPD, drought, precipitation, whatever you're interested in, and some that actually respond positively. And so to think about this, we need to think about how climate varies over time. And so in this hypothetical example, in this conceptual example, we've mapped out what I would call the um, average range of climatic variation in a normal period, whatever that might be. And so it's the gold bars with the filled light magenta. In this situation, if climate varies within this range, most of the trees aren't too threatened or they aren't not too vulnerable to the changes in climate. Maybe some of the blue population could be vulnerable in certain conditions, and maybe some of the orange could be vulnerable in other situations. But in otherwise, most of the population in this example could grow fine, climatically speaking. But of course, we know climate is shifting. And so in this example, climate shifts in such a way that the trees that have correlations between, let's say, minus 0.35 to maybe point to 0.1 they would be rather unaffected. And it's the trees that have the positive correlations, the strong positive correlations that could have their growth and possibly their lives threatened by this climate shift. And in this case, when we're comparing two populations, instead of the mean chronology, which does not represent the full range, the richness of the forest, of all the trees in the forest, more of the blue trees, the trees in the blue populations would be threatened, and some in the orange would be threatened as well. But with this climate shift, more of the orange population would be within the realm, within the envelope of climate. And so in this case, you would say that, well, the orange population is would be essentially more resilient, less affected by a climate shift, and that the blue population would be quite threatened. And then in both populations, though, we have individual trees, and this is where it's important not to make a chronology. We have individual trees that will be just fine. Well, theoretically, you know. And and I think this is important because the more I think about this, trees and dendrochronology, and I was lucky to teach in a biology department, that it's the individual variation, to me, is the grist of ecology, adaptation, and evolution, right? So, Marta was an incredible soccer player, one of the best in the world. What if Marta was the tree or the tree representation, most like Marta, that lived in this range? Why would we sacrifice the knowledge, the experience, the understanding that we would gain from a tree like Marta by distilling it into a chronology and not understanding that some individual trees will actually be okay in this climate shift? And so that's a really important point to me is that we need to study the full range of individuals in the forest, but we also need to study their responses individually and try to understand it from a population perspective. And so that's my introduction before we drop into the world of cross dating. It's nice to be at a conference so I don't have to explain what cross dating is. But with that, I can imagine there might be some people who think, can cross dating really impact our understanding of ecology? There are plenty of papers out there that show that cross dating is important to understand climate shocks, climate change, fire history, individual annual events that we know that happen. Can we do the same with ecology? And of course, I'm going to argue that it is important to the basis of ecology. And so here's an example of my first population level collection that I can think of. It's from a while ago, red maple at the Harvard Forest when I was a grad student. And what you see here, well, first, what I learned when I was cross-dating these red maple is some individual trees had, 2, 3, 5, 7, 9, and one of them had 12 missing rings at coring height. We cored them about a meter or lower above the ground. And so most of these trees were understory or mid-story trees, so they were being suppressed, I think, and they were missing a lot of rings. And so then that got me thinking, what's the implications of that for the carbon cycle, for stand dynamics? Stand dynamics and recruitment are processes that happen surely during a year, but they occur over decades too. And so what I did is I stripped out the missing rings that I could identify from the same set of trees, and I created two populations, a dated population and a misdated population. And what you see when you see the number of trees recruited per year over time, that many of the blue trees were the misstated trees where I took out the missing rings were recruited into the forest just before or after the 1938 hurricane, which was a major hurricane in this region. That would be a very easy paper to write, right? If I don't cross date this and I find that a third of the trees or a quarter of the trees are related to a big canopy disturbance, that makes ecological sense. That's an easy paper to publish, but it would be misleading. It would be incorrect because when we actually date these trees precisely, you'll see that there's a big spike of recruitment actually a decade before the hurricane. I think this is a logging event that set the forest up, that set red maple up to enter to the canopy. There are no trees after the 1938 hurricane that are recruited into the forest, which is not what you would expect. But cross dating shows us that that's not what happened. That the hurricane definitely altered the structure of the forest, but the recruitment of red maple into this forest occurred before the hurricane, with a lot of it occurring in the decade before the hurricane due to a logging event. But I wanted to, I kept doing my research to study disturbance ecology, and I wanted to think about this more. And so what I did is, I was noticing my lab and we were noticing some interesting growth patterns in a couple populations. And what we decided to do is go to the International Tree Data Bank and study populations of trees within the central hardwood region of the eastern United States. So this is a region dominated mostly by broadleaf species. We downloaded 76 chronologies. They're not all broadleaf, but we do have 12 species. So it's a fairly rich um, data set to test this on. And the basic theory of forest development over time in this forest type, in the closed canopy dense forest, is that the stochastic nature, the random individual mortality and recruitment of trees, random in time and space, asynchronous, leads to a rather stable canopy at very large scales. If you only have 1 or 2 or 3% of the forest dying at large scales, the forest doesn't change much over time. That's what the theory says. And so we were noticing some interesting patterns in a couple populations. So we downloaded this data. We did a disturbance analysis of the data to look at inferred canopy mortality, the growth patterns of the rings, growth releases that would be related to inferred canopy mortality. And what we found was this is the percent of trees disturbed per year, so binned annually. This is inferred canopy disturbance between 1650, 1660 and the early 1900s, that there is a massive spike here in 1776. The first dashed horizontal line is 1 standard deviation. The second one is 2 standard deviations. 1776 had 6 standard deviations greater than the mean, a really significant mortality event that was synchronous in time and in space. And in fact, 1776 is of this 5-year period, 1775 to 1780, of a really large synchronous canopy disturbance in this region that's supposed to be dominated by gap dynamics. There are other synchronous events back in time that are 1 and 2 standard deviations above the mean. So there's another part of the ecology of these forests, the development of this forest that we need to think about that challenges theory. And I was lucky that my collegial ancestors, so to speak, the people that made these chronologies, cross-dated them well and made them available in the International Tree Data Bank so I could do the analysis to determine that 1776, precisely 1776, is the big year of mortality across this part of the United States. And so I'm really grateful for their work and especially for their cross dating. Now, let's really talk about the nitty-gritty of cross dating. And let's start with some of the best examples. This is Dr. Amy Hessel of West Virginia University. She was the lead PI of a project that I was on where we were studying the uh, hydroclimatic change in central Mongolia and how it might be related to the Mongol Empire. And we were sampling on lava fields like this one. Mongolia, as you know, is cool, dry. It's actually hot in the summer now. Um, and living on these lava fields, there's very little soil. So these trees are very thirsty. They have a very strong drought signal. And so we took samples from living and dead trees. And let's look at the correlation. Let's look at the growth of these trees over time. So this is ring widths in millimeters on the y-axis between the 40s up to the early 2010s. And you could see there is very synchronous growth, especially in the late 40s to early 50s. There's this period from the late 60s into the early 1980s, where you have highly synchronous growth, and another period in the early 2000s. This is the 21st century uh, mega drought, maybe. I don't, yeah, pretty close to a mega drought. There is variation around the mean. So the individual black lines are individual cores and trees. The orange line is the population mean. And there is individuality in the growth of trees from year to year around the mean, but it's rather synchronous. And let me show you what statistically what this looks like in the in the Cofetcha output. And what you see here is that in 50-year periods, among just five example trees, the correlations are in the point nines. It's ridiculous. There's some correlations out here, 0.95. The weakest one in this group is 0.77 right here. And so putting together this chronology was really kind of easy, if not kind of boring. After a few cores, you knew what to expect. You could cross-date it quickly and easily, and the correlation output is just amazing. This is things we dream about when we make dendroclimatic collections. And that's what I dream about anyways. I can't speak for you. But let's talk about ecology, and let's talk about ecology in closed canopy forests. This is a forest near where I grew up. This is in the Adirondacks in northern New York State. It's a northern hardwood forest that's mixed with fagus and suga, pitsea, acer, and a few other species, but not too many, maybe about seven or eight. And this big tree right in front and center here, just left of center, is sugar maple, Acer saccharum. It's an iconic tree. It gives us great color in the fall. It produces a sugary sap in the spring that we can boil down and have wonderful tree sugar with our food, I have it in my coffee this morning. And it's just a wonderful tree that's important to the culture, the ecology, and the economics of this region. It's really the foundation of a billion-dollar economy in the fall. Cross dating it is very different. It's very hard. So let's look at a spaghetti plot of this population. This is the spaghetti plot for the same period of time, late 40s to early 2010s. The yellow line is the mean, and you can see that there is very few periods of synchronous growth among these trees. There's a period here in the mid 1970s. There's a couple of years, maybe in the late 1990s, early 2000s, and then again around 2010. Otherwise, it's almost every tree for themselves. They're all almost all doing their own thing. There's a common variation that we could distill down into a chronology, but inside the guts of this chronology, there's a lot of what we would say is noise, or what I would say, there's a lot of cool ecology that's happening, a lot of grist that's happening in the ecology, a lot to study and to understand. But let me show you the Cofetch output. Sorry, I laughed because I knew it was coming. So if we look at tree 2084, we can see that on the outer years, it cross-dates the mean chronology in Cofecha really well. 0.81, 0.71, 0.57. These are astronomical correlations for sugar maple. But then when we start getting back to the early part of the record in the mid 1800s to early 1800s, the numbers essentially go to zero. There are B flags, and then the correlation goes to negative to the mean chronology. This other tree, where there's two cores per tree, is doing quite well during the same period, but 2084 does not agree at all. It's really frustrating. I don't remember the story of this particular individual tree, but I do remember that the oldest sugar maple in this population, we spent 2 days trying to cross date it. And it just doesn't agree with the rest of the population very well. But let me take you to a new population of sugar maple that we've collected only in the last 2 years. This is Mosier Reservoir in the same region in the Adirondacks, a big park, about 2 million square kilometers, something like that. Or maybe it's hectares. Sorry, it's hectares. Anyways, these are the wonderful sugar maple here on the right. This is the Cofetcha output of our chronology. Not all the trees, but most of them. And you can see individual cores are correlating at best 0.38 0.42, but we have other individual trees, including one of the oldest, that's correlating essentially at zero or negative. I mean, this we had we had two people working on this specifically, and they were pulling their hair out. They're like, I don't understand what's happening. I can't find the patterns. And so we worked on it very hard for probably a couple weeks or so on this population. And then we said, this is the best we can do at this time. What we did next is actually, oh yeah, let me show you how scary it is on the inside. So, right, so here there are some 50-year periods in the Cofetcha output that correlate quite well. And then there are mostly flags and a lot of negative correlations or correlations that are in the point ones. So this is really a difficult chronology to work with. This is the worst one I think we've worked with so far. But I'm going to try to persuade you that I think we actually have it pretty well dated for most of the time period. And I can say that because what we did then is we took these data and we distilled them into a chronology as Marco Carrara showed us in the 2011 paper that I showed you earlier. And then we compared it to other sugar maples in the region. And when you look at the other sugar maples in the region, we were thrilled, we were excited, we were surprised because in the outer century plus, the correlations to the mean chronology, even in the population Mosier, which is right here, number two, is actually really good. 0 0.6, 0 0.7, 0 0.5, 0.43, I'm really thrilled with sugar maple. And then the correlations decline back in time. When we zoom in on the Mosier Reservoir, the most difficult one that I just showed you, the correlations are really fabulous. And then they get weaker and weaker and they get to essentially zero. And so what's happening in Mosier, and I think what's happening across the region, is we only have two or three or one or four trees in each population before 1800. It's very hard to get trees, sugar maples that are much older than this. That's what we've found in the last few years. And so what I think is it's really hard to cross-date sugar maple within a population when you only have two or three trees. It's really hard. There's a lot of individuality of the tree. And now try to do that across a large region and you get correlations like this. But I'm going to try to convince you that I think we have this dated back to 1800 with certainty. And this comes back to old school dendrochronology. And so we made a chronology of sugar maple, and that's what you're looking at right here across the region. And when we were working with the Mosier Reservoir, another population, Pollywog Pond and Mountain Pond, Jillian, one of our lead technicians, and Zach and I sat down and we went ring by ring studying the rings before 1850. This ring looks like this, 1827 looks like this, 1811 looks like that. And we went back and forth and we studied the rings and we tried to essentially skeleton plot or plot list, the list method to date these cores with our eyes to understand it. And at one point, someone goes, oh, 1816 is a narrow ring. I think it was Jillian said that. And Zach goes, oh, 1816 is an extremely narrow ring in my population. And so we started scrambling and we looked at the populations and we actually found that 1816, I'd like to say a Marta year, is the ring, the pointer year, the marker ring, whatever you want to call it, is the year that locks down our chronology to 1816. It's narrow in two or three populations and the handful of trees that we have. The rings don't cross-date statistically very well in the mid 1800s, but 1816, so far, we want to test it some more, looks like the marker ring for the entire chronology. So I think we can feel pretty good about our dating back to the early 1800s. It was really surprising, and it's really important ecologically because 1816 in the northeastern United States, but in other parts of the world, it's the year without a summer. We had uh, uh, diaries talk about snow or frost or freezing every month of the year, even in our summertime. And so we know the human experience was really bad. We haven't seen much examples of that in the tree ring record, except for Jesse Pearl's work on cedar. This is a major tree species, and we think maybe we have the first evidence of a major impact of 1816 on a major tree species in the Northeast United States. And we only did that because of cross dating, as ugly as it is. And so, how do you hold on loosely to your love and of dendrochronology while not letting go of your understanding of dendrochronology and cross dating? And I want to plead right here that the best way to do this is to learn the chronology. Take your time when you have a new collection, maybe it's a new species, maybe it's just a new collection in a new region. Sit down with the first four, five, six trees and study them very closely. Use the list method, use skeleton plotting, whatever works for you, but learn the chronology. We do digital dendrochronology in our lab now, and I see how easy it is to scan an image, measure it quickly, throw it into Cofettia, and then be confused about why it's not dating. From my experience, I think we need to sit down and learn the marker rings through time. Study the first three, four, five trees. In sugar maple's case, it's a dozen. In the subtropics and the tropics, maybe it's 18 trees. I don't know what it's like. Study the ring patterns and not just the width of the rings, the colors of the rings, damage to the rings, whatever the clues are about each year. Learn the chronology. Invest in yourself, invest in your time, invest in your trees, invest in the chronology. If you do that for the first few days, the rest of the dating and the measuring goes much quicker, is much more efficient, and less frustration. Please, when you can, take multiple cores per tree. One of the things we do to ensure we have dating is we cross-date them internally. And I know that's a basic thing that's in all the basic writings about cross-dating, but this really saves us when we're working with something like these sugar maple trees, right? So quite often we've noticed we'll have two cores from the same tree. They cross-date be sometimes beautifully, sometimes not so beautifully, but they cross-date. We can see the large and small rings through time. And then when we compare it to the rest of the population, one of them looks like it has significant errors in the dating, but the other core dates weakly or okay with the rest of the population. And so we've decided that if one core dates decently with the population and the tree dates internally between multiple cores, it's dated. We can be comfortable with that. It's maybe statistically ugly, but we can move forward with our dating and go on to the next hard tree. And when you're finalizing the chronology, this is an old saying, go back to the wood, which that just means when you're double checking your chronology at the very end and you're working with the most difficult individual trees, go back to the wood and study them like we did for the year of 1816 in sugar maple. That's going to really help you work through some of these individual chronologies. So really study the wood from the start to the end. And then when you have a chronology that you're feeling like, I don't know how good this is, and I've been there many times now, you distill that chronology, distill those tree rings into a chronology, and you check them versus other chronologies. And of course, it's always best to start with the same species. So if you're lucky to have another population nearby, or at least within the region, you can check other sugar maple chronologies. But we don't often have that. And as we're studying the ecology in the Northeastern United States, we're making new chronologies of mostly new species. And so don't be afraid to test other species, a chronology of one species versus the new species that chronology that you're making. We've actually found that trees that have different morphologies and phenologies and successional status and disturbance sensitivities and climate sensitivities, quite often their chronologies cross-date because you're distilling them into the common, strong common signal that Marco Carrara showed us at the beginning of this talk. And so don't be afraid. I know it's not the standard in dendrochronology, but that has saved us more often than not with some of the new chronologies with some of the most difficult species that we've been studying. And lastly, statistics are really important. They guide my work, they guide all of our work, but our brain is a guide too. So when you're working on this, think, examine the wood, reason, and make decisions. with yourself, with a group of colleagues, with your mentors, whoever it might be. This is a team game. This isn't sport, but this is a team game, and it takes multiple people, I think, to work out some of these hardest chronologies. And so to wrap up, I want you to consider that some segments and some trees from ecological collections might not be perfect, statistically speaking. They just might not look good statistically. The correlations are low or negative, but they might be okay because there's so much individual variation in terms of growth and disturbance history in trees that you just have periods where the trees are just affected by something different and they don't cross date in a traditional dendroclimatic sense. But they're cross-dated visually, they're cross-dated statistically in ways they just don't look so great. And that's okay. That's okay. And we need to consider that science isn't human endeavor. We uphold science for a lot of good reasons, right? We live longer, we live healthier. There's so many good things of science. It's a human thing though. And humans, while we're doing our best, sometimes we make mistakes. But I think more often we are confronted with limitations. We're confronted with limitations of our ability to perceive things, to understand new things that don't fit the model that we've been taught. Or one of my technicians, it turns out, has trouble seeing sugar maple rings because of how his eyes work. He struggles with the sugar maple just because of his eyes. And that's not his problem. That's not his fault. That's just who he is. He's really great at what he does. But we are confronted with limitations. The most common limitation in my mind is a lack of replication in these ecological collections for some of the oldest trees. So there actually might be dating errors in some of our chronologies in the very earliest portions where we cannot compare it to other trees and other populations. And we just have to be transparent and honest in our science. Science is a discussion supplied with data and statistics. It's a conversation over time that gets us closer to whatever the truth might be. And so let's keep that in mind and do the best we can when we do our cross dating, because understanding the ecology of the 21st century forest is extremely important. So with that, I'll take any questions you might have. Thank you.
Thank you so much, dear Dr. Neil Pederson. Your presentation very interesting because all the neuro community know how it's work when we are working in this dendro project, especially when we are using a tropical trees. And all your suggestion, recommendation are so welcome for us. And any participant maybe want to make a question, feel free for make this. Yeah, okay, the Dr. Johannes Edwardson.
Oh, thanks a lot, Neil, for a great presentation. Inspiring to see that you can work with messy spaghetti plots and bad statistics in Kufetch. I experienced the same thing when working with peatland trees, and that hydrology often mess up and make very tough conditions for the trees. But my question was what happened in 1776 with this 6 standard deviation tour for 1 year? Must be something really extreme, but maybe I missed it. But what happened? Do you know?
Yeah, I didn't explain it because I was focusing on the value of cross dating. So thank you for that. The best we can reason is, and we found it in the tree rings first, some of it, is there was an extreme frost, May 4th, May 5th, 1774. And I only know the dates now because I talked to Kerry Mock and he said, go look at the Moravian diaries. They will record things and you can understand that. And so we saw this kind of a frost ring in a couple species, a damaged ring in 1774, and it was across genera. And so I talked to Carrie, and we went to the Moravian diaries, and we found that spring came early that year, like almost a month early, and the colonists put their crops in early, and then they had these extremely cold and extremely late frost. And and that was in the middle of a drought that followed several multi-annual droughts in the decade before. So I think it's the compound interaction between extended droughts over time weakening some trees and then defoliation due to this late frost event. The colonists wrote about how the trees in May 1774 looked worse than winter. It looked like death. And so they described really dire situations in this part of the world, and that's the best reasoning we can make. Um, the 1774 ring is the marker ring in that part of the world. And it's narrow and it's missing sometimes, but it's also discolored. It's white colored. And so that's how we clued in on the idea that it was probably some kind of defoliation. And so that in combination with the colonist diaries, and there are a lot of them, Carrie Mock went back into ship logs and all kinds of diaries in the region, and everyone talked about this extreme severe drought, or sorry, frost event that occurred, and then the tree ring record tells us that there were droughts leading up to that. But it's interesting that you mentioned where you're working that you have trouble with some classical cross dating too, because I started as a technician working on trees in Mongolia, and there were some, even in that condition, there were some trees that just did not cross date with the rest of the population. And in the past, we would throw those cores out because they weren't good for climate reconstructions. And what I'm trying to say that I didn't say is those trees are valuable for the ecology. We need to understand all the individuals for the ecology as best we can.
Yeah, thanks for highlighting that. So yeah, I will go back to some of those I thrown out also in the past and double
Yeah,
check what could be the reason. Yeah, yeah,
I'm working on a paper to ask people not to throw out cores for ecological
yeah.
studies.
Okay. Yeah,
Thanks,
yeah.
Peter.
Thanks for a great
Thank you.
presentation. Yeah, yeah,
Nice to meet you.
yeah. You too. Yeah.
Thank you so much, Dr. Johannes Edvardson, for your question. Maybe any participant wants to make other question, please? You
Hello.
are welcome. Yes.
Hello. I'm Malik Malat. I'm from Tunisia.
Okay.
Um,
You're
uh,
welcome.
Thank you. Thank you, Dr. Pederson, for this good presentation. It's so nice. Um, Currently, I'm a master's student in forestry science in Tunisia. I'm currently working on the dendroecological of pine in my region.
Mhm.
So I have some questions because I'm trying to research the correlation between the tree ring growth and the climate.
Mhm.
I do some statistical analysis with R, and I have some problems in the package tree claim. So can you help me to resolve this problem, or there is another solution to treat this one? Sorry, my English is not good enough, but I'm trying to improve it. That's it. Okay.
Yeah, I would reach out to the forum or some of the authors of these things and ask them. They can advise you better than I could. So, but I love hearing what you're doing. I think you're doing really interesting and important work. So, keep at it. But I would reach out to some of the authors of some of these programs, or the tree ring forum online isn't what it used to be, but the different tree ring groups on Facebook and other places can be quite useful and helpful.
So there is another solution to resolve this problem, or I don't know.
It's hard for me to say at this point, without looking and fully understanding what you're dealing with. So I
Okay,
couldn't.
so can I contact you and find your email address?
Sure.
So okay, I will
Thank you.
contact you. Okay, thank
Okay.
you.
Thank you so much for your question, Melek. And thank you so much again for the Dr. Neil Pederson with his interesting presentation here.
I have a question. Can I ask you, Dr. Pederson?
Yeah, okay.
Okay.
Go ahead.
So,
Yeah.
Dr. Pederson, let's assume that I have two forests situated in two forests in the northeastern part of Bangladesh. One forest is situated in the northeastern part of Bangladesh, and other forest situated in the northwestern part of the Bangladesh. And I have selected a species which can be found in this forest, and I let's assume that I have made a chronology from the northeastern part, and I have made another chronology from the northwestern part. So should these two chronology be identical? Should it be identical, or it may not be exactly identical? And can I work on it further climate growth analysis?
Yeah, I don't know if I'd expect them to be identical, and an interesting question is to understand how far a species might cross-date with the trees of the same species across the region. I think that varies in time and space. Um, David Miko's 1993 paper, Spatial Anomalies, is a really foundational paper that kind of hints at this idea, and there's old literature like that. Experiment, try, and see. But I think that you've got something good and workable. But will they cross date? Maybe. I wouldn't expect them to be identical, separated by great distances, but they still might cross date decently. I don't know.
Okay, sir. So if not, I get identical chronology.
Yep.
So then can I go further to climate growth analysis?
Sure. Yeah.
Okay.
Yeah.
Okay, that was the question. Thank you. Okay.
Okay, thank you so much. We have the next presentation for our